Passive and active elements. The power of an element comes in two flavors. One, you could have passive elements. Passive elements absorb energy/power from the circuit. On the other hand, active elements deliver energy and power to the circuit. Understanding when an element is passive or active is all about the sign of the current. Initially, that can be quite tricky. So the way to eliminate the trickiness is that remember our current sign convention. Okay, remember our current sign convention because it's key to identifying passive versus active. So here we go. This is what we said before. I have a current. If this is the positive and that's the negative terminal, and it has some voltage, let me copy this real quick. Then, if the current enters the positive terminal, then we say here that we have a positive current. That's what that is telling us. On the other hand, if the current enters the negative terminal, then we say here that it's going to be a negative current that's flowing through that element. So we got to remember those details. Okay, now that we have that, let's go look at them. Passive elements. As already stated, passive elements absorb power/energy from the power supply. in the language of physics 4b, electric charges lose potential energy as they cross the element. There are two views to conceptualize this. So let's look at that. So our conceptual viewpoint looks like this. So a positive charge naturally slides down the electrical incline and loses electrical potential energy that converts into heat for resistors. So picture-wise, we have an incline. And this incline going to go down to here. And we have our other plate. So if I see that this is positive and this is negative, we typically call this the ground, which is 0 volts, which that's going to be the low. This guy up here is going to be the high. And of course, this height change from here to here is going to be the voltage. So now if I place a charge on here, that charge clearly loses height as it goes down the incline. So if I take an energy viewpoint of this, what we're seeing here in a resistor, once again, we're finding here is that I have electrical potential energy right here. And all of this electrical potential energy gets converted into thermal energy due to the vast number of collisions here. So according to conservation of energy, those electrons clearly lose potential energy. Once again, a charge loses potential energy as it moves from high to low potential. This is passive. That's what we mean by passive. Now, from the elemental viewpoint, right, we said that there was two views. So what about from the element viewpoint? Which is exactly what you should be thinking about. If a current enters the positive terminal, its current is positive. Therefore, charge absorbs power energy from the power supply. So again, picture-wise, we've already drawn this. So let me come and grab this. It's right here. So when I look at this thing, this is what we mean by passive. And you can see here that what this tells us here is that the current here is positive, which then means this. What it says here is that the voltage is always positive. In this case, the current is positive. So if I put this all together, then this tells me here is that if I have a passive power, then that means I have voltage times current, but I have two positive signs, and you can see here that this is greater than 0. So in summary, positive power implies power was absorbed slash dissipated by the passive element. So that's a big deal right here to be able to make that differentiation. So now let's go to active elements. Active elements deliver slash supply power energy into the circuit. Here, a charge gains potential energy when it crosses an element. So let's look at this. So let's start with the conceptual viewpoint. A positive charge that moves from low to high potential. In other words, going uphill, gains potential energy. So again, if I steal from our previous picture over here, I can do this here. So if I place this right here, here's what we're finding here. What is this charge doing here? This charge is moving uphill. How can a charge move away from a negative plate to a positive plate? It can't. So a charge all by itself cannot move up the potential incline. Some non-electrical work or non-electrical force, some non-electrical work must be involved to make this happen. This non-electrical work is associated with the EMF of a power supply. That converts chemical potential. It's not work, but it converts chemical potential into electrical potential energy. So very similar to what we said before, a charge that gains potential energy as it moves from the low to the high potential is active. So that is our definition of what we mean by active. So from the element viewpoint, what do we have? The current enters the negative terminal. So the current enters the negative terminal, and therefore its current is negative. This element increases a boost in power energy into the circuit. So we've already drawn this, so I'm going to just come up here and get it. This is our active element. So if I bring this down here and I paste it, this is what we have. So in this situation, what we're seeing here is that we get something like this. We find here is that the voltage is positive because it has a positive sign. Our current here is negative because it enters the terminal that's negative. So when you look at this combination, this tells us that if we have an active power, we have voltage times current, but then I have a positive and a negative, and you could see immediately that this thing is negative. So an active element has a negative power. Putting this all together, negative power implies power slash energy was delivered slash supplied by the active element. as a follow-up question, is a capacitor active or passive? Capacitors are passive because they do not have an EMF that carries charge from a low to a high potential. They don't. And so picture-wise, this might be disturbing because if I think of a capacitor plate, I could imagine that I have something like this. Let's say that this is my capacitor plate. So if I think of a capacitor plate and it's charged, and let's put that this capacitor is connected to a resistor. Okay. So if this is connected to a resistor, we're going to say that this is a resistor. And in this situation, I have positive charge here, and this is negative. So if I think about this being a capacitor, this field, right? There's a field, a potential field between this capacitor plate. And this capacitor plate here has to have some voltage between these two plates. So that means because there's no EMF, that means that the current of the capacitor is this way, which then immediately tells us that the polarity of the resistor is down. So therefore, the current of the resistor also goes down. That's pretty counterintuitive, but it has to be this way. So the last thing I want to say about power here is I want to talk about conservation of power. We transfer the idea of energy to power. That is, if I think about conservation of energy, we are now going to move this to conservation of power, because the rate of energy per unit time should be the same as conservation of power. Conservation of energy sets certain conditions on a possible circuit. And it is only a condition that cannot be isolated from the other conditions of the circuit. For example, we may need more details that Kirchhoff's laws provide. I'm going to say this again because this is something that happens in circuits that people misunderstand. That is, one cannot solve circuits using conservation of power alone. You can't do that. So what we're finding here is that now let's look at this mathematically. In physics, we know conservation of energy for an isolated system to be the initial energy must equal the final energy. Well, we can do effectively the same thing in conservation of power. Conservation of power implies that all active powers must equal all passive powers. And this can be tricky. Why is this tricky? The reason why it's tricky here is that all energy supplied must be dissipated by the elements. You can't save electrical power. So in our language here, we say that active powers being delivered to the circuit must be absorbed by the passive powers. Once again, what does this statement says? It says that all active powers being delivered into the circuit must be dissipated by the passive element. That's huge. So in other words, in this case, we write it this way, that the total power of the active elements must equal the total power of the passive elements. All of the energy or power being delivered must be absorbed or dissipated by these guys. In other words, we say that then the sum of all active powers must be the sum of all passive powers. This is what conservation of power means.